So picking a buffer for a bit of work relies on us knowing the Ka of the acid, the conjugate acid. This is important, particularly when you deal with basic buffers. When you deal with acidic buffers, you know, it's pretty obvious. You just pick an acid that has a Ka near the pH range you want. But for basic buffers, we have to pick, we use a weak base, but weak bases have even weaker conjugate acids. Remember, as the acidity goes down, the basicity of the conjugate goes up. And so as the acidity goes down, Ka goes down. And so these get crappier and crappier in terms of their acidity. And so you want a basic material to have to be up there. In pH, its conjugate acid is gonna be poor or have a lower pKa. So this is where the Ka pKa transition comes in. So convert mentally or on the calculator. So if you wanted a pH range, you wanted a buffer in the pH range of 9.5 So if you wanted a pH of around 9.5, you would pick a pKa around 9.5. That's just how it works. Again, we can go plus or minus 1 p unit. All right, and so, you know, we could get away with about 8.5, or we can get away with about 10.5. And so if you look at our list here, we see two acids and bases, two acids that are reasonable. In class, I use the cyanide, and I'll use this, the phenol in this particular example. So phenol, C6H6OH, this is the acid form. The basic form, C6H6O minus. This is called phenoxide, sodium phenoxide, or potassium phenoxide, and phenol. You can get these two materials. So how would you prepare a buffer then that has a pH of 9.5? And that comes again from our Ka equation. So this is our weak base. And this is our weak acid. Again, helps to write this stuff down. Conjugate base, conjugate acid. And so we know that we want a target of 9.50. That'll be equal to the pKa, which in this case is 9.89, plus the log of the base over the acid ratio, the molarities of those. And so if we plug this value into our calculator and solve, 9.5 minus 9.89, this is negative 0.39 is equal to log of the base over the acid. And so we can solve this, raise this to the power of 10, 10 to the negative 0.39 is equal to the base over acid ratio. You can do property of logs as well, Merle, all right? So, but, you know, the end result is the same. You get this number. That leads to our ratio. So our ratio here is base to acid has to be 0.4041 is equal to the moles of base, or the molarity of the base, divided by the moles of acid. Or 0.41 moles of acid will equal the moles of base. The moles of acid times 0.41 will equal the moles of base. There will be more acid than there will be base. So as long as we can set this up. So, assuming that we were going to start with 1 mole of acid, this would be mix 1 mole of our phenol and 0.41 moles of our base would give us the right ratio. But we could have started with any moles because this is a fraction. This is a fraction. Another way to look at this, if this 0.41 isn't doing it for you, is that the moles of acid is 2.4 times the moles of base, which is consistent with this ratio. And so one of the simplest way to do this is you dissolve 0.41 moles of the base in 1 liter of water, and you dissolve 1 mole of the acid in 1 liter of water, and you have a ratio. So let's take a look at another example. This one is not in your book, but relies on the same methods. And we're going to use our old friend acetic acid, which has a pKa of 4.74. And we want to make a pH equal to 5. It's equal to 4.74 plus the log of the base, which in this case is sodium acetate, divided by the acid, HOAC, says that if we wanted to make this solution, the ratio would have to be fixed by this. So the ratio, the log of this number, this ratio would give us 0.26. The anti-log of 10 to the 10 to the 0.26 is equal to 1.82. And so 1.82 would be equal to the acetate to acetic acid ratio. Pretty much where we ended up last time. So if we were making a liter of this, we take a mole of this, and we take 1.82 moles of this and 1 mole of this. But that's kind of wasteful if you needed a smaller quantity. Okay? But this is a mole ratio. This is a mole ratio. So as long as we know the number of moles of HOAC, we can figure out the moles of acetic acid now. So, if you wanted to create a ratio where you're dumping in sodium acetate into a solution that was 0.1 molar, and you had 100 mils of it, of the HOAC, as long as we have this fixed ratio, if we know the moles of acetic acid, we then can figure out the moles of sodium acetate needed. Well, and that's pretty simple. Well, we have a volume and a molarity. We know that for every 100 mils, that is equivalent to 1,000 mils is 1 liter, and for every 1 liter, this is our molarity statement, that is 0.100 moles of HOAC, so that in this solution, there's 1 times 10 to the minus 2 moles of HOAC, so I just need to have 1.8 times as many of that. Because of this ratio says that 1.82 AC, as long as it's equal to 1 or more. So, now where you have to be cautious is flipping these numbers. you have to remember that this is a ratio of moles of OAC to moles of acetic acid. So even though it looks like you would multiply moles of HOAC over here and you would get acetic acid, this in reality, though, the units are already here. This is an X and a Y. There's no units here. So this number is really 1.82 moles of OAC minus over 1 mole of HOAC. That's what that ratio says. So this is actually not a 1-to-1, and so if you multiplied this over here, that would give you the wrong setup for this. So just remember that the log of this ratio, this is a mole ratio already, and so we don't actually know those coefficients. And so that's why you notice it coincides with these units here. We know that this is 1 times 10 to the minus 2 molar. HOAC cancels, and we are left with 1.82 moles of 1.82 times 10 to the minus 2 moles of sodium acetate. And once we have that, uh, 1.5 grams of NaOAC drop down into this 100 ml solution of acetic acid should give us the correct pH. Now we can check. We now have our grams of NaOAC. We can convert that back into moles of NaOAC. And we can drop that into 100 milliliters, and you would get a molarity for the NaOAC. And then you started with a 100 ml solution of 0.1 molar acetic acid. And so we know the molarity of that. And those two molarities should be, the molarity of this should be 1.82 times 10 to the minus third, should be 0.182 molar for the sodium acetate. You could check that ratio, and you'll find that is the truth.